Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in.
Okay, so our first question here is explain how a gas exerts a pressure on a container. So basically, there's kind of a set mark scheme that you need to learn for this kind of question. So the first things first, you have to mention that it is the gas particles colliding with the walls of your container that are therefore exerting a force on your container. So that's the first thing. You could then mention, because there are loads of gas particles hitting the container, it's like that force is constant because you have that large number of collisions with your container wall. This isn't something I'd usually mention in my answer, but it is part of your spec, so I'm going to mention it here. The force that is exerted on your wall is 90 degrees to the sides of the wall. And then finally, don't forget to link the idea of force back to the original question, which was about pressure. And you do it by just listing this equation in your answer and saying, since pressure is force over area, as there is a force on the walls, there is a pressure in my container. Okay, next question. You take a fixed container of gas and measure the pressure inside of the container. State and explain what happens to the pressure of the gas if it's moved to a warmer room first and then to a colder room. So when it says you take a fixed container of gas, what it's telling me is that my gas is going to remain at a constant volume because my container has a constant volume. So you should know that when you heat those gases up, you're increasing the temperature of your gas, which is going to increase the average kinetic energy of your particles. And since you've increased the average kinetic energy of the particles, what you've actually done is make them on average move around quicker. And this is the key line, more frequent collisions with your container. So that key word frequent there, or in other words, your particles are hitting the sides of the container more times per second. Because of those more frequent collisions, you have a larger overall force on your container. And again, linking to pressure is force over area. A larger force gives me a larger pressure. Now, the second part of the question was what happens if I take it into a colder room. I'm not going to write it all out again. It's basically the opposite. Decreased temperature, decreased average kinetic energy. They move around a bit slower, your particles, less frequent collision with the walls, less force, less pressure. Okay, how would you describe the relationship between gas pressure and temperature, and is it true for both units of temperature? Okay, so if I'm thinking about my relationship between the pressure in my gas and the temperature of my gas, what comes to my mind first is thinking about the graphs that we have. So we have this pressure temperature when we have our temperature in Kelvin, and this pressure temperature graph when our temperature is in degrees Celsius. So what I'm basically seeing from these graphs and what I know about increasing the average kinetic energy of my particles when I increase the temperature is that I get this linear relationship. As temperature increases, pressure also increases. So what's the difference between temperature in Kelvin and temperature in degrees Celsius? Well, I have this bit here where my graph, if I'm in Kelvin, is directly proportional because it is going through the origin. But if I'm in degrees Celsius, then it's not directly proportional because it doesn't go through the origin. So that's the difference. And remember that bit where my graph is crossing my x-axis for degrees Celsius, that will be at minus 273 degrees, or my absolute zero temperature, which is 0 degrees Kelvin, which is why your pressure temperature graph in Kelvin goes to the origin at 0 Kelvin. Okay, so in this question we've been given a table, and it says how to use the table to prove that pressure and temperature in Kelvin are directly proportional to each other. So firstly, on the left there is written the mathematical relationship if it were true. So temperature, and that sign alpha, means is directly proportional to pressure. And another way of writing that that's going to be helpful to us is temperature is equal to some constant, which I'm calling K, multiplied by pressure. So that's what I'm trying to prove. If I can prove that every time I take a temperature and its respective pressure, they are related via this constant K, and that constant remains the same throughout my table, then I can prove these two things are directly proportional. So don't ignore in a question like this, when they've given you a table, they want you to actually use figures and numbers from the table. So I'm going to take two different rows of the table. I'm going to take this one and this one, just choosing those two rows randomly, and I'm going to write them out following this equation I've got here. So I'm going to assume that it's true. T is equal to K times P. So for the first row, I've got my temperature 173 is equal to K times 36, and that gives me my constant K as 4.8. That's just dividing 173 by 36. So let's do it for the next two numbers in my table in that row, and let's see if it's true for them as well. So 273, my temperature, equals K times the pressure, 56.7. And if I divide 273 by 56.7, I get my constant K to be 4.8. So I could do it a few more times, and every single row that I take, I'm expecting this constant K to be 4.8. And that tells me, yes, since this constant K is a constant, these two things are directly proportional. So that's quite a maths heavy way to prove these are directly proportional. The other thing that you can do looking at the table, if you're not happy with that, is let's look at our temperature here. This seems to be our independent variable because it's our first column, and see how we were changing the temperature in this experiment. So if I look at each change in temperature, I will find every time I'm increasing the temperature by 50 degrees. So I'm going up in those equal increments of 50 degrees. If these are directly proportional, what I'm expecting is that as I go between each of these pressure readings, 36 to 46.4, 46.4 to 56.7, 56.7 to 67.1, and so on, that all of those increments should be roughly the same. And if I do it, if I check the difference between all of those pressures, I see that they are roughly the same. They seem to be going up in 10 kilopascals every single time, so it's the same increment. So that's another way to prove that these are directly proportional. Okay, so I've got my same table here, and now I'm being tasked with how do I use the table to find absolute zero. Now, first we need to remember what absolute zero is. So that is the temperature at which the pressure of my gas would be 0, because it's the temperature at which my particles are not moving. If they're not moving, they can't collide with the walls, they can't exert a force on the walls, there can't be any pressure in my container. But if I look here, I don't have a figure in my pressure column that is at 0. So what I would need to do is plot this graph. Pressure and temperature in Kelvin. And what I'd plot is the black part of that line there, which ends at some point where my temperature is 173 and my pressure is 36. Okay, that's my lowest pressure that I have from the data in my table. Then what I've done with my green line is I'd have to extrapolate that line back, following the same trend until I reached 0 pressure. And if I do that, I should find that that happens at my origin, where my temperature is 0 degrees Kelvin. Okay, so now we're on to gas pressure and how it's affected by volume. So which scenarios have a fixed volume of gas, and how do the following things affect the pressure in the gas? So the first one, you have a sealed syringe and you're pushing it down. So by a sealed syringe, that would mean that one end was the plunger where you push it and the other end is closed or sealed shut, so no air can escape basically your syringe. So if you push the plunger down, what you are doing is effectively changing the volume of your container. You're changing the volume or the space that those particles can occupy, those gas particles that are trapped in there. So you're changing the volume, and if you're pushing the plunger down, you are decreasing the volume, and we should know as we decrease the volume, we increase the pressure in our gas. If I want to then explain why, I say the following things. There's less space, so you have more frequent collisions of your gas particles with the walls of the container because they have less space to move around in. So if you have more frequent collisions, you have a larger overall force. Since pressure is force over area, that is a larger overall pressure as well. Okay, next one, a balloon rising up into the atmosphere. Okay, so again, we're imagining that our balloon has been tied and is sealed, but you may know that as a balloon would move up in the atmosphere, the balloon actually expands. So since the container, which is the balloon, is changing size, it's expanding, but because I'd sealed the balloon, there were no extra air particles coming in and out of the balloon, then I have changed the volume, okay, because I've changed the container that the gas is in. And what have I done to the volume? Well, how would I know that it's expanded rather than contracted? It's because I know as I go up into the atmosphere, the pressure decreases and therefore the volume increases. Larger volume, so you have less frequent collisions of your gas particles inside of your balloon with the walls of the balloon, so there's a smaller force on your balloon, and pressure is force over area. So as that volume gets bigger, the pressure gets smaller because of these less frequent collisions. Okay, finally, releasing some particles from a cube container and then shutting the lid again. So be careful here. Some pupils get confused between the idea of your gas particles and how many of them there are, or the mass of your gas, and the volume of your gas. When we're talking about volume, we're talking about the volume of the container. So what I'm doing here, as I open my container and then shut it again, I keep the same volume. I keep the volume of my container the same, but because I've released some gas particles into the air, I've let some of the mass out. So you might say to yourself, well, if you keep the volume the same, then you keep the pressure the same. But that's when we are assuming that the mass of the gas has also remained the same. So we need to now think logically about what is going on here. So it's not that you have a smaller volume of gas. The volumes remain the same because the container has remained the same. But you do now have less mass in your container because you have fewer particles, and since you have fewer particles in your container, they will be hitting the walls less frequently overall, so you'll have less frequent collisions and a smaller pressure. So be careful here. This one's the most confusing example because it's not really to do with your volume and your pressure here at all. You kept your volume the same, you actually changed the mass of your gas, which will affect your pressure as well. Okay, time to look at a Boyle's law example. So a gas is in a container with a volume of 5 centimeters cubed and a pressure of 80 kilopascals. What's the new pressure in pascals if the gas is moved to a container of 12.5 centimeters cubed? Okay, so my equation, as always, let me just write it out to begin with. P1V1 equals P2V2. P1 being my initial pressure, which I've been given in my question. My initial pressure was 80 kilopascals, and V1 being my initial volume, which was given to me in my question as 5 centimeters cubed. P2 is my new pressure, that's what I'm trying to find, that I'm not sure of yet. And my final volume is 12.5 centimeters cubed here. So what I'm going to do first is I'm just going to write all of these P1, V1, P2, V2 into where they should go in my equation below. So P1 80 times V1 5 is P2 times V2 12.5. Notice here how I haven't converted anything. I haven't put my pressures into pascals. I haven't put my volume into meters cubed like you might expect me to do. This is one of those times in your GCSE where not only is it possible to leave these in the units that they give you, it makes your life a lot easier as well. And it's to do with the fact that you're multiplying these things together. So that's going to be one of my top tips later. Remember, for this equation, you actually don't need to do any conversions. Okay, so we just write this out like this. And then on my left-hand side of the equation, 80 times 5 is 400. And on my right-hand side, P2 times 12.5. So to get P2, I divide 400 by 12.5, and that gives me 32. So what I do need to remember to do, since I haven't converted any of my units yet, is whatever my pressure was given to me in the question, which was kilopascals, that's going to be the unit of the pressure that pops out on the other end. 32 is kilopascals, not pascals, because I wasn't converting any of my units. So now I do need to take an extra step because my question has asked me what is the new pressure in pascals. Since it's 32 kilopascals and there are 1,000 pascals in each kilopascals, that's 32,000 pascals. Okay, now on to some graphs. So sketch graph how pressure varies with volume of a gas and explain the shape of the graph. So make sure you do this right. Make sure you've got pressure and volume. I've been quite naughty here. You should include some units as well, really. So maybe pressure in pascals and volume in meters cubed, but it depends what units they give you. And I'm sketching a curve downwards. Don't be tempted to put a straight line downwards. These are inversely proportional to each other. As pressure increases, your volume decreases, but that does end up giving you a curve. Okay, so remember that. Don't be tempted to put a straight line downwards. And I can write that mathematical relationship like this: P times V is equal to constant. So like I was doing before, when we had that table and we were relating the pressure and temperature, and we had P equals a constant times T, for pressure and volume we actually have P times V equals a constant. So if they asked you to try and prove that pressure and volume were indirectly proportional to each other, you could use this equation and find that constant K being the same. Okay, it's not what they've asked us to do here though. We need to explain the shape of the graph. So we say, well, as the volume increases, the pressure seems to be decreasing. Why? And at this point, I feel like a broken record. Less frequent collisions, smaller force, so smaller pressure. Okay, let's have a go at using our pressure temperature law. So on the left here, we have a gas has a pressure of 400 pascals and has an unknown original temperature. It's heated and it then has a final temperature of 400 Kelvin and a final pressure of 1.5 kilopascals. What is the original temperature? So P1, our original pressure was 400 pascals. T1, the original temperature we don't know, we're trying to find out. Our final temperature was 400 Kelvin and our final pressure was 1.5 kilopascals. Now, I've converted that by multiplying by 1,000 into pascals, so 1,500 pascals. It's not always necessary to convert these things. However, what I do need is I need my two pressures to have the same unit. At the minute, one's in pascals, one's in kilopascals, so I definitely have to convert one of them. So I converted the kilopascals one, and now they've both got the same unit of pascals. I can use my equation P1 over T1 equals P2 over T2. and plug the right things in the right place. 400 over T1 is 1500 over T2, 400. And then on the right hand side, I'm just going to do that, plug that into my calculator. So 1500 divided by 400. So this simplifies to 400 over T1 is 3.75. And then I need to multiply both sides by T1 and divide both sides by 3.75. So I get 400 divided by 3.75. That gives me T1, and that is 107 Kelvin for my temperature. Okay, next question. A gas has a temperature of 450 Kelvin and an unknown original pressure. It's heated, it has a final temperature of 500 Kelvin and a pressure of 8 atmospheres. What is the original temperature? So T1 is 450, that original temperature. P1, I'm trying to find out. I don't know my original pressure. And then T2 is 500 Kelvin, and P2, it's been given to me as 8 atmospheres. Now, don't worry, you don't need to go, oh no, how do I convert atmospheres into pascals? It's absolutely fine. It just means if we leave it in atmospheres, whatever P1 comes out as, I will have to quote in atmospheres as well. So P1 over T1 equals P2 over T2. Let's put the things in the right place. P1 over 450 is 8P2 over T2, 500. Again, do that right hand side first, the 8 divided by the 500. So this simplifies to P1 over 450 is 0.016. And therefore P1 is, well, I multiply both sides by 450, 7.2. And that is in atmospheres because the P2 pressure that I plugged into this equation was in atmospheres. So a gas has a pressure of 4 atmospheres and a temperature of 56 Celsius. What is the final pressure? Sorry, the final pressure is 6 atmospheres. What is the final temperature in Kelvin and then in Celsius? Right, P1, 4 atmospheres, and I'm just going to keep it like that. T1. So whilst for your pressures, you can have them in any unit as long as the two pressure units match. For your temperature, this is an equation that only works for your temperature in Kelvin. So that requires you to know or remember how to convert your degrees Celsius, 56, into Kelvin. But really, it's rather straightforward. You just add 273 to it. That's in Kelvin. And then let me write my other things out. My P2, my pressure 2 was 6 atmospheres. And so I've got P1 over T1 is P2 over T2. P1 4 over T1, if I add 56 to 273, I get 329 equals P2 6 over T2. I'm trying to find out. And then I do the left-hand side there. 4 divided by 329. And once I rearrange by doing 6 divided by that, I get my T2 is 493.5 Kelvin. Now it's asked me to also state the final temperature in degrees Celsius. So now I've got it in Kelvin, I can convert that temperature into Celsius by minusing 273, and that gives me 221 degrees Celsius. Okay, so you can convert back into Celsius, but I could not have plugged that 56 in as T1 and got out my T2 to be 221. It would not have worked. So make sure all of your temperatures are in Kelvin before you use this equation.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets and completely for free, so why not?
The first one, volume versus mass of a gas. Yes, just be very careful when we're talking about pressure changing because the volume's changing. We're talking about the volume of the container, and we have to assume with our pressure temperature or our pressure volume relationships that one of the things that's remaining constant is the mass of the gas. If the mass of the gas is not remaining constant, then that's going to complicate things further because either we've got more or less particles in our container as well, and we need to think about how that would affect the pressure. So volume of the container is what we're talking about. No need to convert for Boyle's law. Yeah, remember you can just shove in if pressure's in kilopascals, that's fine. If volumes are in litres, centimetres cubed, whatever, that's absolutely fine. Just remember the value that you get out will match the unit of whatever value you put in. So if your volume 1 is in litres, your volume 2 will come out in litres as well using this equation. There is a set mark scheme for changes in pressure, whether it's due to temperature or volume. You need to mention basically the frequency of the collisions and what's happening to the frequency of the collisions, either because you're changing the temperature and therefore changing the average kinetic energy or speed of your particles, or because you're changing the volume and therefore changing the space that your particles are moving around in. And finally, using your table and graphs for relationships, remember to take data directly from your graph or from your table if it asks you to try and prove one of these relationships between these different variables in your gas.